wanted to teach a little bit of a topic which I feel is something I want to learn, but I cannot actually do it because I'm not in the field. If I was in the field, I could have probably done it, but I'm not in the field, so I don't know. But I still wanted to teach a little bit and learn a little bit on my own too. So this is Murali Shastri's someone told me this is good. So it's a mathematical introduction to robotic manipulation, which is by Richard M. Murray and Sigali S. Shastri and stuff. I don't really think there is anything special about this book, but I just wanted to check it out and maybe teach a little bit. So, robotics, let's go. So, it was made by playwright technically, but because eventually they always turn against the creator and annihilated the human race. That's what always happened. So, this is the first of all the Stanford manipulator. I'm not actually sure what it is, so let's see. Primitive when compared with expectations created by Newton and began after World War II in developing control manipulators. Argonne and Oak Ridge National Laboratories, handling radioactive material. Master manipulator guided by the user through a series of moves that were depicted by a slave unit. Slave unit was coupled to the master through a series of mechanical linkages. Either electric or hydraulic powered teleoperators. So they were made by General Electric and General Mills, and force feedback to keep the slave manipulator from crushing glass containers was added to teleporters, teleoperators. So this is the Cincinnati Milacron T3. It is an industrial robot, heavy payload, process applications and all it could do. The CNC machine tools for accurate milling of the low volume, high performance airplane parts was done. George DeWard made the first one. PATD. Joseph Engelberger founded Unimation and installed its first robot in General Motors plant in this time. So the program could be retooled and reprogrammed at a relatively low cost so as to enable it to perform a wide variety of tasks. So Unimation robotic arm was a departure from design. Open kinematic chain was used, had a centrally leveled beam structure, many degree of freedom was there. Created a large number of problems since many degree of freedom was there, and it created a lot of problems because difficult to accurately control the endpoint of a cantilevered arm and also to regulate its stiffness. Errors at the base of kinetic chain tended to get amplified further and out into the chain. So if there is a kinetic error in the base of the chain, it would be amplified further out. To alleviate this, hyaluronic actuators, both high and high precision, were used. This is programmed PUMA, Universal Manipulator for Assembly. Unimation's PUMA. Ernst in this time developed a robot for forcing sensing using stack blocks. It used an unstructured environment lead to creation of man and computer at MIT. Tomovic and Boney developed a pressure sensor for the robot which enabled it to squeeze on a grasped object and develop one of two grasp pattern. Binary robot vision system also to respond to obstacles in the environment was developed. So Stanford manipulator, Boston arm, and EMF, American Machine Foundry arm, and Edinburgh arm were also introduced around this time in 1968. So they can listen to voice commands and stacked randomly scattered blocks, and they can do all the stuff. Japan also they came in this time with Kawasaki's acquisition of a license. So this is the Adapt 1 robot, and this is the CMU DD arm 1. This is also the ADEX 1 ADEX 1 6-legged walking robot. So language for programming robot motion called Wave was developed at Stanford to enable commanding a robot with high-level commands. Cincinnati Electronic Incorporated also introduced the T3. Could lift 100-pound load as well as track objects moving down on an assembly line. Paul and Bowles showed how assemble water pumps, and Will and Gossman touch and force sensors to enable a 20-part typewriter. Draper Laboratories put together a remote control RCC device for part insertion in assembly. So you have programmable universal machine for assembly based on a General Motors study. SCRA was introduced in Japan and then in US. So electrically powered weapons and robots were used for reasons of relative inexpensiveness and cleanliness. And electric motors, maximum power, relatively high speed, and they can be geared down for use. It introduces friction, backlash, and expertise to design of the motors. So the search was a way to make designing motors directly without the need to get geared down into the motors. It was developed at Carnegie Mellon by Asada in 1981. So 1980s, several efforts was made to improve the performance of industrial robots in fine manipulation act. Active methods using feedback control and improved precision accuracy, and programmed compliance, and passive methods include mechanical redesign of the arm. It is when not a period of great innovation in terms of building new robots. Understanding the algorithms, trajectory planning, and sensory aggregation of robots was required. So, effective recursive Lagrangian and computational schemes for computing the gravity and Coriolis force in time of active dynamics. This was done. This is active control methods. You have exactly linearizing the dynamics of multi-joint robots by a state feedback using a technique referred to as computed torque. So computed torque also was developed. So it was to provide linearizing the dynamics of a motor joint robot. Computed torque. Okay. So it also involved exact cancellation. In practice, had to be done either approximately or adaptively. Robot links were getting to be lighter and to have harmonic drives rather than a gear trains in their joints. So this made flexible joints and arms. In turn, necessitated the development of new algorithms for flexible link and flexible joint robots. 90s had been modified for different assembly operation. Robot World manufactured by Automatics, which featured several 4 degrees of freedom modules suspended in air with a Sawyer effect motor. Modules could have been modified for assembly task at hand. Robots were working in hazardous environment. Great strides had been made. Planetary exploration, hazardous waste mobile, mobile robots and all was made. Reconfigurable robots and robots are hazardous environment where we feel that field of robotics is primed today for some large sensor and actuator technology. So we need actuators and sensors technology. The milli and micro scales. So we currently use 6 joints which are either rotatory, articulated or sliding, prismatic with simple end effect for interacting with the workpieces. So application range from pick and place operation to moving cameras and other inspiratory equipment to performing delicate assembly involving matting parts. There is nowhere near the fanciest stuff as early fiction, however. But welding, painting, transportation of material, assembly of printed circuit boards, repair, inspection in a hazardous environment, all can be done. So the term hand or end effector is used to describe interface between the manipulator and the environment. Hand or end effector. Out of anthropomorphic intent, vast majority of the hands are simple. You can have grippers, pincers, tongs, or in some cases remote compliance drivers. So the grippers can be 2 or 3 jaws, pincers are 3 hands, 3 fingers, tongs will be 2, and remote compliance devices not sure. They are designed on ad hoc basis, specific tasks, whatever required specific work, you just put it off. They have suction cups for lifting glass, not suitable for machine parts or jaws. They cannot handle fragile parts, however. So they also compressed as air for holding metallic parts, but not suitably for handling fragile parts. Okay. For the difficulty that is commonly encountered in the application is the clumsiness of a 6 degree of freedom robot. Because there is a lack of dexterity, simple grippers enable the robot to hold parts securely, but they cannot manipulate the grasped object, and limited number of possible grasps result in need to change and effectors frequently for the different tasks. So large motions of the arm are sometimes needed for even small motion of end effector. Since motors of the robot are progressively larger away from the end effector, motion of the earliest motor is slow and ineffective. So lack of fine force control with limits assembly tasks to the most rudimentary ones. So a multi-fingered articulated hands often offer some solution to the problem of handling with dexterity and versatility. Yeah, so this is how a human works, model context. So a multi-fingered hand to reconfigure itself for performing a variety of different grasps reduce the need for changing end effectors. Lightweight actuators with degrees of freedom of hand allows a fast, precise, energy efficient movement of the object held in the hand. Multi-fingered doesn't truly answer Yeah, honestly, I'm tired. That's more than enough. I just wanted to check it out.